In this video, we're going to do an optimization problem in which we're given a piece of sheet metal, 60 by 30 meters, and asked to make a rectangular box with an open top. And we want to determine dimensions that'll give the box the largest volume. So what we do here, we start with a piece of sheet metal, and we're going to cut a square of X meters from each corner, as you'll see in the next slide. Okay? When we do that, it allows us to imagine this rectangle that I'm drawing now as the base of an open top. And then all of these shaded regions are sides that we're going to flip up to create the box. And there doesn't need to be a top because that literally tells us we're going to have an open top. Okay? So when we do that and we flip up those sides, we're going to see that because this original side length was 60 and we cut out X from all the corners, that now that side length of the actual base of the box will no longer be 60. It'll be 60 minus an X on the left and minus an X on the right. In other words, 60 minus 2X. And this side length, this one I'm shading in now, that'll be 30 minus 2x. So the actual area of the base of that box will be 60 minus 2x times 30 minus 2x. Now, when we flip up all these heights, where I'm shading in now, all of those are going to represent the height of the box. Well, that's equal to x, so the height of the box will be x, and so we can come up with a volume formula for the box itself, which is going to be, you can see the box drawn there. We can see that the volume of a box is obviously going to be length times width times height. Well, we established the length is 60 minus 2x, the width is 30 minus 2x, and the height is x. So we actually, after expanding things out and collecting up some like terms, we see that our volume as a function of x is equal to 1800x minus 180x squared plus 4x cubed. Well, if we can imagine a domain for this question, we're going to be easily able to determine the maximum possible volume. Well, let's talk about that domain. We have to cut two x's from both a 60-meter side and a 30-meter side. To determine the maximum possible value for x, let 60 minus 2x equals 0 and let 30 minus 2x equal 0. Well, if 60 minus 2x is 0, then x is 30. If 30 minus 2x is 0, then x is 15. Well, we have to be able to do both. And so if we made an x value of, let's say, 20, which allowed us to fit within this domain, it wouldn't be useful to us because the maximum we can cut on the widths is 15. So in other words, what I'm trying to say is we see that we have to respect the 15 here and say the maximum possible value for x is 15. But we can imagine theoretically cutting square lengths of 0 or virtually 0 out of each corner and flipping up minuscule sides as well. So we can see that our minimum value for x will be 0, our maximum value for x will be 15. And so we come up with a domain given here, 0 less than or equal to x less than or equal to 15. You might justifiably also say 0 less than x less than 15. So when we do that, we have our volume formula with our domain written out right here where we've circled it. So we want to determine the derivative of our volume formula and set it equal to 0. When we do that, we get 12x squared minus 360x plus 1800 equals 0. Well, that's not going to be solvable with integers, so we can rely on our quadratic formula, and we'll see that x is either equal to roughly 6.340 or 23.660. Luckily, this question tells us we can round to 2 decimal places. Rounding to 2 decimal places is great. Let's round to 3 decimal places before we get to the end of the solution. Well, we see that x had to be a number between 0 and 15, so this value of 23.660 is going to be thrown away, but we will keep the value of 6.340. That one's fine. So what we do is we imagine x equal to 0, and we determine what the volume would be using our volume formula. We imagine x equaling 6.340, and we see that our volume would be roughly 5,196.15, and we let our x be 15, and we see our volume would be 0. So we can see that our greatest possible volume occurs when x is roughly 6.340. Now, that would, since x is 6.340, our length would be 60 minus 2 times that, which is roughly 47.32, and our width would be 30 minus 2 times that, which is roughly 17.32. Our height was actually equal to x, so that would be the 6.340. And so rounding to 2 decimal places, we can say that the dimensions leading to the greatest volume of the box in these circumstances have the dimensions listed on our therefore statement at the bottom of the slide.